Welcome back to the online lecture series on chemical applications of group theory. So this session is tagged under the code L01/A3 and is all about symmetry elements and various symmetry operations. A molecule may have one or more symmetry operations. Sometimes it may have as many as infinite number of operations. But regardless of all these number of operations, there are only 5 symmetry elements, and every symmetry operations will fall under the one of these 5 type of symmetry element and corresponding symmetry operation. So let's discuss the first symmetry operation, which is identity operation. And this operation is usually represented by the symbol E, and this letter E comes from the Greek word einheit, meaning unity. And this symbol tells you to do nothing. The operation is sometimes known as do nothing operation, or it's a kind of rotation by 360 degree, which is equivalent to doing nothing, right? So that's why this symbol, this operation is called a do nothing operation. Then if a molecule possesses this symmetry alone and no other symmetries, then the molecule is called asymmetric molecule. And do nothing operation definitely exists for every object because the object itself exists. So one immediate question that comes in our mind is why we have included this operation in the list of symmetry operations. Actually, we need this operation only to satisfy certain mathematical requirements of a group. You might have seen in the second session of my lecture that a mathematical group should contain an identity element, right? So in order to qualify a group as a mathematical group, it needs an element which commutes with all other elements, and that element is known as identity element. So in our case also, in molecular symmetry, we need an element which commutes with all other elements, and that is none other than this identity element E. That's why we have included E to the symmetry operations group. Okay, let's come to the second one, which is a reflection, and the symmetry element in this case is a mirror plane. And the symbol used to represent a reflection operation is by the lowercase letter, Greek letter sigma. A molecule is said to possess a plane of symmetry if a reflection through an imaginary plane in the molecule leaves the molecule indistinguishable from the original configuration. So accordingly, if a molecule possesses a mirror plane, it can be bisected by that plane. So immediately you can say that any planar molecule is bound to have at least one plane of symmetry. Why? Because all atoms lying in the plane does not move at all during the symmetry operations, right? So it should have at least one plane of symmetry. It may have more than one plane of symmetry, but it should have at least one plane of symmetry. So you should keep in mind that any planar molecule is bound to have at least one plane of symmetry. Now suppose that if an atom that do not lie in a plane, then in order to have a plane of symmetry, there should be a similar atom on the opposite side, on the negative of itself. Or in short, we can say all atoms of a given species that do not lie in a plane must occur in even numbers. Let's take the case of methane. You can see that one atom is away from the plane. If you take this plane, one atom is out of the plane, and you can see the same atom on the other side of the reflection plane, right? So this is what I said, all atoms of a given species that do not lie in a plane must occur in even numbers. Now what happens if I do the reflection operation about a plane twice? So the effect of applying same reflection operation 2 times, we can say that it brings all atoms back to the original position. So mathematically we can say that sigma operation multiplied by a sigma operation will lead to identity operation, or sigma square is equal to E. So the combination of reflection operation twice on a particular plane takes the molecule to the identical or original configuration. Thus, any mirror plane is associated with only one unique operation, that is sigma. And if you do sigma twice, that is sigma into sigma, it leads to identity. Now what happens if I do the sigma 3 times? It is equivalent to sigma square into sigma, right? So that is exactly equal to sigma. So let's take some of the real-time example by considering some of the small molecules and count the number of symmetry planes. Let's take the first example. This example is a sulfur compound. Central atom is sulfur and we have a double bond oxygen. We have a bromine atom here and we have a chlorine atom here. So this is a kind of pyramidal molecule, and looking at this molecule you cannot find any symmetry planes associated with this molecule. So this molecule is an example for a molecule that doesn't contain any reflection plane. Now consider another molecule. This molecule is an ethane derivative, and looking at this molecule also, you cannot find any reflection planes associated with this molecule. So this is another example for a molecule that doesn't contain any symmetry plane. Alright, now let's take another example. This example is an ethylene derivative, in which we have one chlorine atom on one carbon and one bromine atom on the other carbon atom. This green is chlorine. Now since the carbon atoms are sp2 hybridized, all atoms should lie in a plane, right? And we all know that every planar molecule should possess at least one plane of symmetry. Now if I draw the plane, this is the plane of symmetry associated with this molecule. Since it is a planar, it should at least have one plane of symmetry in which all atom lies in the plane, and that plane is known as molecular plane. So this is an example for a molecule that contains one symmetry plane. Now let's go to an example where two planes of symmetry exist. And one favorite example is water molecule, and this is the water molecule, and central atom is oxygen, and water has a bend shape. Now we have seen the water molecule contains only 3 atoms, and hence it should lie in a plane, and immediately you have a plane of symmetry in which all atoms lies in that plane, right? So this is the first plane. So one plane is along the molecular plane, and you can immediately assume the other plane which bisects this molecular plane. So it's perpendicular to the molecular plane. So if I draw the second plane, this is perpendicular to the molecular plane. This is the molecule. This is the second plane. So this is the other plane. Now the reflection through this plane leaves oxygen atom unshifted and the other 2 hydrogen atoms exchanged. If we see the animation, we see that the reflection leaves the oxygen atom unchanged in position, and the other 2 hydrogen atom gets exchanged, right? And what about the first plane? In the first plane, reflection through this plane leaves all atoms unshifted, right? If I reflect, it doesn't undergo any change. So we have 2 perpendicular planes associated with water molecule. Now let's take another example for a molecule which again contains two planes of symmetry. It's a bit bigger molecule. It's bromobenzene. Now if you see bromobenzene, all atoms in this case also lies in a plane. We know that benzene is a planar molecule. So all atoms of bromobenzene lies in a plane. So this is the molecular plane, and this is one plane present in bromobenzene. What is the other plane? Other plane is perpendicular to this plane such that the plane goes through the carbon-bromine bond, right? So this is the other plane. Now if I do a reflection through this plane, the atom contains the plane gets unshifted while the other atoms are exchanged. And you can see the hydrogen atom goes to a position where there is exactly the same atom lying there, and a carbon also, and hence it possesses a plane of symmetry, and that is perpendicular to the molecular plane. So these are the two planes associated with bromobenzene. Let's consider another example for a molecule which contains two planes of symmetry, and in this case it is cis-1,2-dichloroethene. And we know that this molecule should also lie in a plane because the carbon atom in this compound is sp2 hybridized, and hence all atoms should lie in a plane. Immediately you can say that there should be a plane that contains all atoms, which is the molecular plane. This is the molecular plane, and there is another plane which bisects this molecular plane in the middle, and this is the other plane present in this molecule. So this molecule has two planes of symmetry. One is this one, and other is the molecular plane. If I reflect all atoms through this plane, you can see that all atoms gets shifted and gets exchanged with the same atom. Now there is another example. This is ammonia, and you know ammonia is a pyramidal molecule, and ammonia is an example for a molecule which contains three planes of symmetry. In ammonia, the central atom is lifted upwards a bit, and this causes the molecular plane to be absent when compared to planar molecules like BF3 and all, right? Now this is ammonia. Let's see what are the three planes. The first plane is along the central nitrogen atom and one of the hydrogen atom. This one. This is one plane. And you can see that, immediately see that due to its symmetry, we have another plane that cuts the central nitrogen atom and the other hydrogen atom, and the third one cuts the other hydrogen atom and central nitrogen atom. These are the three planes of symmetry. Now if I reflect the molecule through this plane, atom lying on the plane, that is the central nitrogen and one of the hydrogen, gets unshifted, whereas the other two hydrogen atom gets exchanged. So you should keep in mind these 2 points. Any planar molecule is bound to have at least one plane of symmetry, as the atoms lying in the plane does not move at all during the symmetry operation, right? And another thing, as in the case of ammonia here, all atoms of a given species that do not lie in a plane must occur in even numbers. That is, here you can see that one of the hydrogen atom that does not lie in a plane, so there should be a similar atom on the other side. Otherwise this plane of symmetry will be absent. Okay, now go to another example. Here, in this case, I have taken an interhalogen compound, bromine pentafluoride, and this molecule has a square pyramidal shape. Central atom is bromine, You can expect the number of reflection planes to be 4, right? One of the reflection plane is this, in which it goes through 3 fluorine atom and 1 central bromine atom. Every plane contains bromine atom. So this is one plane. And what is the other plane? The next plane is perpendicular to this. This is the other plane, right? So 2 planes, one is this one. These 2 planes goes through 3 fluorine atom and the central bromine atom. If I reflect this molecule through this plane, you see that there are 2 atoms away from the plane that gets exchanged. Now the similar reflection happens to the other plane. Now there are 2 other sets of plane. One plane goes in between the 2 fluorine atoms. It goes through the central bromine atom and the fluorine atom which occurs on the top. So this plane is actually called a dihedral plane. I will talk to you about different planes later, a little later, maybe after discussing the axis of symmetry. That would be much better. And there is another plane that is exactly perpendicular to this plane. This is also a dihedral plane, and we have how many planes in total? Total we have 4 planes. 2 of these these 2 planes are called dihedral planes, and the other 2 planes, these 2 planes are called vertical planes, represented by the letter sigma V, and the dihedral planes are usually represented by the letter sigma D. I will explain the difference between sigma V and sigma D a little later. Now come to another example. In this case is a trigonal planar molecule, borane, BH3. Since the molecule is planar molecule, immediately you can say that there is a plane of symmetry which bears all 4 atoms, right? So this is one plane of symmetry. And in BH3 or this planar BF3 or whatever this trigonal planar molecule, this plane is usually called a horizontal plane. So we have 3 different planes. One is horizontal plane, other one is vertical plane, and the third one is a dihedral plane. So this is the first plane. And what are the other planes? This is one plane. The plane, and that plane is perpendicular to the horizontal plane that I have just now shown you, this plane. So it is perpendicular. Now you see that 2 hydrogen atoms are away from the plane, and that gets exchanged when I do the reflection. In ammonia, since the molecule is pyramidal and the molecule contains only 3 planes, here we have 4 planes, and the 3 planes are vertical planes, one is horizontal plane. Now consider the case of phosphorus pentachloride. We know that phosphorus pentachloride is a trigonal bipyramidal molecule. Looking at this structure, you can immediately say that there is a plane that contains the 3 fluorine atom and the central phosphorus atom, right? So let me show you the different planes associated with phosphorus pentachloride. This is one plane. And we have 3 other planes as in the case of boron trifluoride. One is this plane, the other one is perpendicular to that, and the third one is again perpendicular. So if I remove the first plane, you will see that we have these 3 planes and a plane that is perpendicular to all these 3 planes, which is later you will see that that plane is known as horizontal plane. So these are the 3 planes. If you take one plane and carry out the symmetry operation, you see that 2 atoms are away from the plane and they gets exchanged. Now this is one example for a molecule which contains 5 planes of symmetry, and the molecule is a coordination compound, tetrachloroplatinate. A central atom is platinum and the other atoms are chlorine atoms. So since it is a planar molecule, definitely you have a plane of symmetry that contains all atoms, and we can say that it is a molecular plane. And what are the other planes? There are 2 sets of plane again. One set of plane passes through 3 atoms, central platinum atom and the other 2 chlorine atom, and the other plane is perpendicular to this plane, and these 2 planes are called vertical planes. And we have 2 other planes that is perpendicular to these 2 planes. One plane is going in between these 2 planes, and you see that it is actually bisecting the angle between chlorine, platinum and the other chlorine atom, and hence it's a kind of dihedral plane, detailed about which I will be discussing maybe later. And the other plane is this one, right? So we have 4 of this kind of plane, and one last plane is perpendicular to these 4 planes. See, so we have 5 planes of symmetry in the square planar molecule tetrachloroplatinate. Now coming to our favorite example of benzene, we have 12 atoms in benzene, and all 12 atoms are lying in a plane, and benzene is a planar molecule. It's a highly stable molecule, and since it is a planar molecule, we will have a plane of symmetry in which all atoms lies in this plane. So this is a plane of symmetry, right? What are the other planes? You can immediately say the other planes. There are 2 sets of other planes. One set is passing through 4 atoms in benzene and is perpendicular to the molecular plane. See, this is the molecular plane, and our new plane passes through 4 atoms in benzene. And what happens when we do a reflection operation through this plane? It goes to a configuration indistinguishable from the previous configuration, and hence it is a symmetry operation. So this is a reflection plane. Now what are the other 3 planes? One is perpendicular to this, and the other one is this one. These are the 3 planes, one set of 3 planes, and there are 3 other planes that will be in between these 3 planes. If I show you the first one among this is this plane. It's called a dihedral plane. This is one of the dihedral plane, and the other one is this, third one is this. So benzene has 6 planes of this kind, and one is perpendicular to all of these 6 planes. So there are 7 planes of symmetry present in benzene molecule. Now let's take a little more complex symmetry molecule, and the first one is methane molecule, which is tetrahedral. This is much more symmetric than all other molecules that we have discussed so far, and this methane molecule possesses 6 planes of symmetry. The first plane, which passes through 3 atoms, central carbon and the other 2 atoms. Now similarly, we have 6 symmetry planes, and in all cases you see that this reflection plane passes through 2 bonds, and hence we have 6 planes of symmetry in methane molecule. Now we will take one last example for a molecule which is called a buckyball, C60 buckyball, which contains 60 carbon atoms and forms like a buckyball shape. Finding the symmetry elements, reflection planes, is not very easy for this molecule, and I would simply say that there are altogether 15 planes of symmetry associated with these buckyballs. I will show you one of the plane. This is one plane that passes through the buckyball molecule, and if we reflect along this plane, what happens is it goes to a configuration indistinguishable from the previous one. Similar to that, we have 15 different planes associated with buckyball, and all are shown here. So let's take one last example for a molecule which contains infinite number of symmetry planes. One favorite example is acetylene, and if you look at acetylene, which is a linear molecule, any plane that passes through all the 4 atoms is a symmetry plane. If I show the plane something like this, any plane that cuts this molecule along this cylinder, so it's a symmetry plane, right? So it has an infinite number of symmetry plane. A plane that cuts all the atoms in any angle is a symmetry plane. So acetylene contains infinite number of one kind of symmetry plane. This molecule also contains one symmetry plane that is horizontal to, that is perpendicular to this cylindrical plane, passes through the middle of the carbon-carbon bond. Okay, now let's go to the other kind of symmetry operation, which is inversion. The third one is inversion and is represented by the symbol I, and the definition has already been discussed. So in terms of Cartesian coordinates, the action of an operation, that is the inversion operation, that transforms the coordinate xyz into their respective negatives, that is minus x, minus y and minus z. So under the inversion operation, the 2 points x, y, z and minus x, minus y, minus z are geometrically equivalent. And the molecule that possesses the I symmetry or center of symmetry are called centrosymmetric molecules. Now if you apply the inversion twice, what happens? So mathematically showing if doing an inversion twice is equivalent to doing the operation I twice, right? So I into I operated on the general Cartesian vector x, y, z will be given by I into minus x into minus y into minus z, right? So again, if you do an operation, it becomes negative of negative x, negative of negative y and negative of negative z. So that leads to the identical configuration. Thus applying the inversion twice will lead to identical configuration, or I square is equal to identity. In short, we can say that if we do the operation n times, so that is I raised to n, then it leads to the inversion I itself if n is odd, otherwise it leads to the identity operation. So you should always keep in mind that center of symmetry generates only 2 operations, the inversion operation and the identity operation. So the unique operation is I. Now let's take some examples for molecules possessing center of inversion. The first molecule is acetylene itself. If you see acetylene, the inversion center is the center of carbon-carbon bond. This green color shows the inversion center. It's not an atom, it's an inversion center. So if I invert all atoms, that means if I translate each and every atom through this imaginary center to the opposite side for an equal magnitude, then you will find the same atom in that position. So this is an example for a molecule that possesses center of symmetry. There are many other examples. Say for example, all homonuclear diatomic molecules like hydrogen, nitrogen, oxygen, etc. all possess a center of symmetry, right? So these molecules are called centrosymmetric molecules, and centrosymmetric molecules are important in spectroscopy as well. Now, the other examples like carbon dioxide, acetylene that is shown here. If you see carbon dioxide, this molecule also possesses an inversion center, right? Where is the inversion center? Inversion center is the center of the carbon atom itself. So carbon dioxide is one example for a molecule that contains a symmetry, inversion symmetry, and in this case the inversion occurs in the center of the carbon atom itself. So if there is an atom in the center, that atom must be unique. In this case, carbon must be unique. Unique in the sense that it should be the only one in the molecule that is not shifted by inversion operation, right? All other atoms must occur in pairs. There are many other examples. You can find some examples in my notes. If you want to get my notes, you have to go to my website, and the website is given in the description box. In the website you can find my notes and many other examples for molecule that contains inversion symmetry. Okay, so let's go over to the next kind of symmetry, which is a proper axis of symmetry or proper rotation axis, usually represented by the symbol capital C subscript n, which indicates that the rotation about an axis by 2 pi by n or 360 by n bring the object into an equivalent configuration. Here the n is known as order of rotation, and SEN operation is commonly referred to as n-fold rotation, and its corresponding element is known as n-fold rotation axis. A rotation axis usually contains several rotation operations. That means it gets repeated several times. Then if it is so, the structure must eventually brought to a configuration identical to its original configuration. That is, the structure will be rotated to a full circle to its starting point. So if the number of rotation repeated is represented by the integer n, see the n is an integer, then we can write n into the angle of rotation theta in radians is equal to 2 pi. So n is equal to 2 pi by theta, which is equal to 360 degree by theta. Here the n is what I have used to call as order of axis, and the axis is given by the symbol Cn. Now this n can have numbers starting from 2, 3, 4, etc. And if n is equal to 2, the axis is known as C2 axis, or it's also known as a dyad axis. And if n is equal to 3, it's known as a C3 axis or a triad axis, and so on. Okay, so now let's take an example of linear molecule, carbon dioxide itself. We have seen the reflection planes associated with carbon dioxide already. Now let's find out the axis associated with carbon dioxide, right? When carbon dioxide is rotated through any angle along the oxygen-carbon-oxygen bond, say this axis, you can see the axis here. If I rotate carbon dioxide along this axis at any angle, it looks the same, right? And hence we say that carbon dioxide possesses a C infinity axis. So the axis along this line is usually represented by C infinity, where the order is infinity. The infinity and the number infinity is given because there are infinite number of indistinguishable configuration that is possible along this axis, right? If I rotate it through 1 degree or 2 degree or 5 degree or a fractional degree, every rotation is a symmetry operation. So carbon dioxide possesses a C infinity axis. Apart from this infinity axis, carbon dioxide also possesses axis perpendicular to this axis. Let me show you those axes here. If you see the axis, there are a large number of axes. I would say infinite number of axes. If I rotate it through 180 degree, if I rotate say along one line, if I rotate it through 180 degree, it goes to an indistinguishable configuration. right? So it has a C2 axis. One of this line is a C2 axis. Each line is a C2 axis. So the carbon dioxide possesses two kind of axis of symmetry. One is C infinity axis, and the other one is infinite number of C2 axis perpendicular to this C infinity axis. So this shows an infinite number of C2 axis. Each axis is a C2 axis that is perpendicular to Cn axis, and you can have as many as infinite number of this C2 axis perpendicular to the C infinity axis. Now let's come to another example, which is also a linear molecule, and is hydrogen cyanide. This is nitrogen, carbon, and this is hydrogen. Since it is a linear molecule, you can always say that every linear molecule will possess a C infinity axis. So here, which is the C infinity axis? It is the axis along nitrogen, carbon, hydrogen bond. So this molecule possesses a C infinity axis along this line. Does this molecule has a C2 axis perpendicular to C infinity axis, as has been seen in carbon dioxide case? No, right? Because two atoms other than the carbon atoms are different, right? One is hydrogen and the other is nitrogen. In carbon dioxide, apart from the central atom, the other two atoms were same. Here it is different. So hydrogen cyanide possesses only one axis. That axis is C infinity axis, that is along the bond axis, and it does not possess any other axis of rotation. Now let's come to the case of hydrogen peroxide. And we know that hydrogen peroxide has an open book structure, right? And in the last case we have seen, in the case of reflection, hydrogen peroxide doesn't possess any reflection plane. That has already been discussed. Now this hydrogen peroxide has a rotation axis. Can you find the rotation axis in hydrogen peroxide? See, it's an open book structure. Through the center of oxygen-oxygen bond, in this way, it possesses a kind of C2 axis. That means if I rotate it through 180 degree like this, if I rotate the molecule along this axis through 180 degree, it goes to a configuration indistinguishable from the original configuration, and hence it is a symmetry operation, right? Hydrogen peroxide contains one C2 axis. Now take the case of a water molecule. Water molecule possesses one two-fold axis of symmetry, and you can see that axis goes through the oxygen atom and in between two hydrogen atom. If I rotate the molecule through 180 degree, it goes to a configuration which is indistinguishable from the initial configuration. Now if I do the C2 operation twice, what will happen? If I do the C2 operation twice, it is known as C2 square operation. And C2 square operation is an identity operation actually, because it goes to a configuration that is identical to the original configuration. So C2 two times leads to identity operation. And water molecule does not contain any other axis of symmetry. Now take the case of ammonia. We know that ammonia is a pyramidal molecule, right? It should have an axis that passes through the nitrogen atom, and the center of the triangle that is formed between these three hydrogen atoms, right? So this is the axis. So if I rotate the molecule through this axis, see what happens. If I rotate it through 120 degree, it leads to a configuration that is identical to original configuration. So in ammonia, rotation by 120 degree is an symmetry operation, and that operation is known as C3 operation. If I do it twice, that is rotation. Rotation by convention is a rotation in the anti-clockwise direction, right? So if I do the anti-clockwise direction twice by 120 plus 120 degree, then again I will get a configuration that is also a symmetry operation. That is also through the same axis C3, and hence it is known as C3 into C3, which is equal to C3 square. If I do it 3 times, then it leads to identity operation. Okay, now let's take another example, C4 operation. And for that I am taking a new molecule, which is tetrachloroplatinate. This molecule is planar and contains a C4 axis that is perpendicular to the molecular plane. So which is the molecular plane? This is the molecular plane, and we have a rotation axis which is called the C4 axis that exists in this molecule. So rotating by 90 degree leads to an indistinguishable configuration. Now if I do the rotation by 90 degree, what happens, you can see that it goes to a configuration which is indistinguishable from the original position, right? Now if I carry out 2 successive C4 rotations about the same axis, which is usually represented as C42, which has the same effect of a single C2 operation, right? That is, rotation, 2 successive 90 degree rotation is equivalent to a single 180 degree rotation. So normally C4-2 operation is usually written as C2 operation. Now if we continue with the third C4 rotation, then we arrive at a new equivalent configuration, which is same as we would have obtained by a single 4-fold rotation in the opposite direction. Now finally, if we perform a 4th C4 rotation, then the molecule will be brought back into its identical position. So that is usually represented as C4 raised to 4, but C4 raised to 4 is equivalent to identity operation. So C4 raised to 4 is usually represented as identity operation. So in general, any Cn rotation carried out n times in succession will carry the object back into original configuration. That is, Cn raised to n is equal to identity operation. So what are the unique symmetry operations associated with the C4? Now we have a C4 raised to 1, which is usually represented as C4 operation. Then we have a C4 square operation, which is identical to C2 operation, right? Then we have a C4-3 operation, which is otherwise represented as C4 raised to -1, inverse 90 degree operation. The fourth operation is C4 raised to 4, which is just identity operation. Now we have 2 unique operations associated with the C4, which is C4 raised to 1 and C4 raised to 3. C4 raised to 2 is equivalent to C2 operation, and C4 raised to 4 is equivalent to identity operation. Now take another example for a molecule which contains 2 different kind of rotation axis. So I'm going to take boron trifluoride molecule. This is shown here. And we know that boron trifluoride is a planar molecule, and there exists a horizontal plane of symmetry, something like this, right? In this molecule, which is having a little bit higher symmetry operations possible, now for this molecule there is a C3 axis that is perpendicular to the sigma reflection. That is this reflection plane. You can see the axis is perpendicular to this reflection plane. Now if I rotate along this axis perpendicular to this reflection plane through an angle of 120 degree, you can see that the molecule goes to a configuration indistinguishable from the previous configuration. Right? So it is a symmetry operation. So there is a C3 operation. Correspondingly, you will have a C3 square operation, which is exactly equal to C3 inverse operation. So rotation clockwise by 120 degree and rotation anti-clockwise by 120 degree, both are the symmetry operations associated with C3 axis. Now, apart from this C3 axis, there are some other axis that is perpendicular to this C3 axis. Say, for example, look at this C2 axis. If I remove the C3 axis, this is a C2 axis, and if I rotate it through this C2 axis, it goes to a configuration indistinguishable from the previous orientation, right? So this is a symmetry operation, and you know that is perpendicular to our C3 axis, this axis. Now you can immediately say that there are two more C2 kind of axes. Each goes through a central atom and one fluorine atom. What are the other C2 axes? One is this one and the other is this one. So how many axes are possible for this molecule? There are 4 axes of symmetry in this case. One is a C3 axis and other are 3 C2 axes perpendicular to the C3 axis, right? So this one. All C2 axis is along the plane, perpendicular plane, and C3 axis is perpendicular to this plane. So this is an example for a molecule which contains more than one axis of symmetry. So boron trifluoride possesses a C3 axis perpendicular to the molecular plane and 3 C2 axes passing through each boron-fluorine bond. Now there is a term called principal axis, which is the highest order rotational axis in a molecule. So here in this example we have a boron trifluoride, which is a planar molecule, and we have seen it has a molecular plane, rotation plane, and that is this plane. And perpendicular to this plane we have a rotation axis, which is a C3 axis. That means rotation along this axis through 120 degrees is a symmetry operation. That is this way, if I rotate it through 120 degree, it leads to a configuration indistinguishable from the original position. Now, apart from this C3 axis, there are other axes that are present in this molecule. One of these axes is a C2 axis along one boron-fluorine bond. Now we have another C2 axis pass through the other boron-fluorine bond, and there is another C2 axis passing through the other boron-fluorine bond. So we have 3 C2 axis that is perpendicular to this C3 axis, right? All the C2 axis is perpendicular to the C3 axis. So you can see here the C3 axis, and which is perpendicular to all other C2 axis. So here we have seen that there is an axis, C3 axis, which is the highest order axis, and this highest order axis is the principal axis for this particular molecule, boron trifluoride. So if we have more than one rotation axis present, and the principal axis in that case is the highest order rotation axis. Alright, now I had already told you that there are different kinds of reflection planes, right? So to discuss the 3 different kind of planes, reflection planes, let us take the case of an example, benzene. Benzene, we know that benzene is a planar molecule, so there will be a plane that containing all the atoms like this. So this is the plane that is present in benzene and which is said to be the molecular plane. We also know that there is an axis perpendicular to this plane. What is that axis? That passes through the center of benzene ring, and if I show the axis, this is the axis. So I have a C6 axis that passes through the center of the benzene ring, and there is a plane, reflection plane, that is perpendicular to this axis, and such a plane is known as a horizontal plane. So this plane is a horizontal plane. So a horizontal plane is a plane that is perpendicular to the principal axis of rotation. Now we know that the axis that I have told you just now, that is a C6 axis, is actually the principal axis for benzene, and the reflection plane is known as a horizontal plane. Okay, now this reflection plane, that is the plane perpendicular to the principal axis, which is usually represented by the letter sigma h. H is in the subscript. So horizontal planes are usually represented by sigma h. Now for benzene there is only one horizontal plane, and that horizontal plane is shown here. Now benzene contains other planes as well. So first one is the horizontal plane that is shown here, and there are two other planes which are known as vertical mirror planes represented by the letter sigma V, and dihedral mirror planes represented by the letter sigma D. So let me show you what are the two other planes of symmetry. So this is a sigma H plane. Now there is one plane that is known as sigma V plane. Now this is a plane that is perpendicular to sigma H plane. If I show you sigma H plane here, you see that two planes are perpendicular. Now this plane, that is the plane that contains the principal axis of rotation and is perpendicular to the horizontal plane. Such planes are known as vertical planes, sigma V's, and this is a sigma V plane. And now you can say that there are three such planes. One is this one, other one passing through the other four atoms, and this is the third one, right? So these three are known as vertical planes of symmetry. Now there are three more planes of symmetry that passes in between these three planes. They are known as dihedral planes. So I will show you one dihedral plane here, this one. So in this case, in the case of benzene, both sigma V and sigma D occur together, right? So in such case, the distinction between the two type of symmetry, that is sigma V and sigma H, is made by defining sigma V to contain greater number of atoms or to contain a principal axis of a reference Cartesian coordinate system, that is either x or y axis. So in our case, in the case of benzene, sigma V and sigma D is made, the distinction is made by defining sigma V to contain greater number of atoms. So if you look at this, one plane contains 4 atoms, other plane doesn't contain any atom. So one is sigma V, which is sigma V, the one that contains largest number of atoms is sigma V, and the other one is sigma D. And if you look at both the sigma V and sigma D, both of them contains the principal axis. Whether a sigma V or sigma D, you can see here, they contains the principal axis, and both of them are perpendicular to sigma H plane. This is sigma H plane. You can see it is perpendicular. Now one more thing you have to keep in mind, that knowing whether a plane is sigma V or sigma D is not a crucial thing to applying symmetry arguments to physical problems. So in benzene, we have three different type of planes. One is sigma H, that is perpendicular to the principal axis, and other one is sigma V, that is that contains the principal axis and passing through maximum number of atoms, and the other one is sigma D, that is the again that contains the principal axis, but it is bisecting only bonds, not through atoms. So benzene contains 7 planes of symmetry. Now coming to the last symmetry element or operation that has to be discussed is a special kind of symmetry operation which is known as rotation reflection or improper rotation. And the element is known as improper axis. The symbol used for improper rotation is capital S subscript n, where n is the order of rotation. And unlike all symmetry operations discussed so far, the improper rotation is a compound operation, meaning that we have to carry out 2 operations in succession. And these 2 operations are, first one is the proper rotation, which is followed by a reflection in a plane perpendicular to the rotation. Now the molecules possessing improper axis of symmetry is generally classified into 2 types. The first category belongs to molecules that possess both Cn axis and sigma H operations. In such molecules, Cn and sigma H operation exist independently. Now we can take one example for explaining this category. Now example shown here is cyclopropane, and this molecule contains a C3 axis and a perpendicular sigma H plane, and hence this molecule should contain an S3 axis. So that S3 axis is this. So what we have to do? We have to rotate it by 120 degree and then reflect. If we do both operation together, it becomes a symmetry operation, and that symmetry operation is known as S3 operation, improper rotation through an angle of 120 degree, right? In this case, both C3 and sigma H is present. Now let's take another example. So the example shown here is benzene, and we have already seen that benzene contains a C6 axis perpendicular to the molecular plane, right? And since it's a planar molecule, it should have a plane of symmetry, and that plane of symmetry is perpendicular to this C6 axis. So this molecule should contain an S6 axis. S6 means C6 operation into sigma H, right? So this is another example for a molecule which contains both Cn axis and sigma H plane. Now the second category of molecules which is having Sn axis are those molecules which have neither Cn axis nor sigma H operations present. And to explain this kind of symmetry operation, let's take the example of allene. So this is the structure of allene, and we know that allene is a cumulated diene, right? So the two terminal hydrogen atoms, terminal carbon atoms that are sp2 hybridized, and these carbon atoms are planar, and these two planes formed between carbon atom and the two hydrogen atom on each end is twisted 90 degree away from each other. So let's see what are the different symmetry operations associated with allenes first. Then I will explain the improper rotation present in this molecule. So the first plane associated with allene is this plane, which contains two hydrogen atoms away from the plane, and all other atoms are within the plane, right? There is a perpendicular plane, that is this one, and there is an axis which is a C2 axis. Yes, there is a C2 axis that passes through the three carbon atoms, right? If I rotate it through 180 degree, this operation leaves the configuration indistinguishable, and hence there is a C2 axis. So this is the C2 operation. Now perpendicular to this C2 operation, there are two other C2 operations. One is this one, is perpendicular to that one, and if I rotate through 180 degree, it becomes a C2 operation. Now there is another C2 operation perpendicular to these two C2 operation, and if I rotate it through 180 degree again, it goes to a configuration indistinguishable from the original configuration. So these are the three C2 axes which can be assumed as a Cartesian coordinate x, y, z, and hence this allene molecule has three C2 axes, and there are two mirror planes. And now these two mirror planes are known as dihedral planes rather than vertical planes. These are known as dihedral planes. And the reason is because these two planes are perpendicular to the C2 axis, that is perpendicular to the first C2 axis, right? This C2 axis. If I show the C2 axis alone, and you see that the two vertical planes are perpendicular to the other two C2 axis. That is why it is known as a sigma D plane. Sigma D plane. We have the C2 axis here, and there is no perpendicular plane, right? If I put a plane perpendicular to this C2 axis, that does not belongs to a symmetry operation, right? But if I reflect the molecule through this perpendicular plane, and then if I rotate it through 90 degree, or if I do the other way around, if I rotate by 90 degree and reflect it through this plane, then it becomes a symmetry operation. See, keep in mind that 90 degree rotation, that is C4 rotation, is not a symmetry operation for this molecule. Sigma H operation also is not a symmetry operation for this molecule. But the combination of these two becomes a symmetry operation. Let's see how this works out. So what I am doing is, I am first rotating through 90 degree and then reflecting. Or I can do the other way around as well. I can first reflect and then rotate. Now this belongs to a symmetry operation. So this is one better example which doesn't contain a Cn axis or sigma h, but it contains an Sn axis, right? So this is the operation, 90 degree rotation and then reflection. So in the case of improper rotation axis, the two cases that we have discussed demonstrate that an Sn axis must exist if there is a Cn axis and sigma h operation exist in a molecule. At the same time, an Sn operation may also exist if neither Cn axis nor sigma h exist, right? These are the two categories that we have discussed. Now, just like the proper rotation, a series of improper rotation can be performed about the same axis. Meaning that improper axis generates a series of operation which is usually represented by the letter S subscript n superscript m, S and m. And each operation consists of a rotation through an angle theta or 2 pi by n followed by a reflection perpendicular to this axis. Mathematically, we can represent this as Snm is equal to sigma h to the power m Cn to the power m, right? Where n is the order of rotation axis and m is an integer that represents the corresponding operation. Now suppose that if m is odd, that is a superscript m is odd, then sigma h to the power m will be equal to sigma h itself. Now suppose that n is equal to m. That means the subscript and superscript are the same. Then Sn to the power m is equal to Sn to the power n, which is equal to sigma h into Cn to the power n, right? But Cn to the power n is identity, so the result is sigma h. This implies that the symmetry plane must exist independently of improper axis if n is equal to m. Now, if m is equal to n minus 1, that means we are considering the next to last operation. Then in such case, the improper rotation can be written as Sn to the power n minus 1, right? Which is equal to sigma h to the power n minus 1 into Cn to the power n minus 1. But since n is odd, we are considering odd improper axis. Since n is odd, n minus 1 will be even. So sigma h to the power n minus 1 will be identity. So this leads to the result of Cn to the power n minus 1. Now if m is equal to n plus 1, that means we are considering n plus 1th improper rotation. In such case, the improper rotation can be written as Sn to the power n plus 1, which is equal to sigma h to the power n plus 1 multiplied by Cn to the power n plus 1, right? But since n is odd, n plus 1 will be again even and sigma h to the power n plus 1 will be identity, and Cn to the power n plus 1 can be written as Cn to the power n into Cn to the power 1, which is equal to Cn to the power 1. The above two results shows that for Sn to the power m operation, a proper symmetry axis should also exist. Therefore, for an Sn axis of odd order should generate both the symmetry plane and proper axis independently. But this is not always the case for Sn axis of even order. What I am talking about is Sn axis for odd order only. Now let us examine some improper axes and their corresponding operations. The first operation consists of rotation through 90 degree followed by a perpendicular reflection. That is the operation associated with an S4 axis. The first operation is S4 to the power 1, which is equal to sigma h into C4 to the power 1. This is simply S4 to the power 1 itself. For the second operation, S4 to the power 2, which is equal to sigma h square into C4 square. But sigma h square is identity and C4 square can be written as C2 to the power 1. So that is equal to C2. That is, carrying out an S4 operation in succession has the effect of a single C2 operation about the same axis. Therefore, we can say that S4 is collinear with a C2 axis. Now, if we continue our operation, the next operation is S4 to the power 3, which is equal to sigma h to the power 3 into C4 to the power 3, which is equal to sigma h into C4 cubed, which is equal to S4 to the power 3 itself. So it has a unique operation. Now the next operation is S4 to the power 4, which is equal to sigma h to the power 4 into C4 to the power 4. Both are identity operations, right? So the result is identity operation. Therefore, the unique operations associated with S4 are S4 to the power 1 and S4 to the power 3. And the operations S4 to the power 2 and S4 to the power 4 are equivalent to C2 operation and identity operation respectively. Now let us examine the operation associated with an S3 axis. So the first operation is S3 to the power 1, which is equal to sigma h to the power 1 into C3 to the power 1, which is none other than S3 to the power 1 itself. The next operation is S3 square operation, which is equal to sigma h square into C3 square, which is equal to identity into C3 square. That leads to C3 square operation. Now if we continue our operation a third time, that is S3 to the power 3, which is equal to sigma h to the power 3 into C3 to the power 3. So that is equal to sigma h into identity, which is equal to sigma h. And you see that S3 to the power 3, or in general Sn to the power n, is not an identity operation if n is equal to an odd number. So we will carry out further operations. Now let's do S3 to the power 4 operation. So that leads to sigma h to the power 4, C3 to the power 4. So that is equal to identity into C3 to the power 1. So that is equal to simply C3. The next operation is S3 to the power 5, which is equal to sigma h to the power 5 into C3 to the power 5. That is simply equal to sigma h into C3 to the power 5, which is same thing as S3 to the power 5. Now if we carry out one more operation, which is S3 to the power 6, which is equal to sigma h to the power 6 multiplied by C3 to the power 6, right? And both of these operations are identity, so the result is identity operation. Thus we see that S3 improper axis generates 6 operations, which may be consolidated as 2 C3 operations, that are C3 to the power 1 and C3 to the power 2, and 2 S3 operations, that is S3 to the power 1 and S3 to the power 5, and there is a sigma h operation, and the last one is identity operation. So there are 6 different operations. So in general, an improper axis of odd order n implies the independent existence of a proper axis of order n, as well as a symmetry plane perpendicular to the proper axis. Therefore, you can immediately say that if n in the Sn operation is even, then Sn to the power n is identity. If it is odd, then Sn to the power n will be sigma or sigma h, and Sn to the power 2n will be identity operation. You can keep these points in mind. Now I shall wind up the discussion on improper rotation by taking one last example of S2 operation. It's a special kind of operation. Now S2 operation consists of rotation through 180 degree followed by refraction perpendicular to the rotation axis. So let's assume that we are applying operation on a general Cartesian coordinates xyz as shown in the figure. Now I am applying S2 operation on this point and see what happens when S2 operation is carried out on this particular point. I'm not taking it as a molecule. Let's take it as some point on the general Cartesian coordinates xyz. Now the S2 operation, first S2 operation is S2 to the power 1, right? S2 to the power 1 is sigma h to the power 1 into C2 to the power 1. So if I apply this operation on the general Cartesian point xyz, then S2 to the power 1 operated on the Cartesian vector, let us take it as a column vector xyz, then what happens is S2 to the power 1 into xyz is sigma h into C2 into xyz, right? So operation has to be carried out from left to right. So we have to apply C2 operation on the general point xyz. So if I rotate it through z axis, this point on x, y, z changes from x to minus x, y to minus y, and z doesn't change because I'm applying the operation along z axis. So it becomes minus x minus y z. We are left with one more operation, which is sigma h. So sigma h operation takes the general Cartesian vector minus x minus y z to minus x minus y and minus z. Because we are applying the reflection perpendicular to z axis, then z component also changes from plus z to minus z. So all the component, in effect, all the component changes from positive to negative. So S2 operation on the Cartesian component x, y, z leads to its negative, minus x minus y minus z. Now if I separately do an inversion operation on the same point, inversion operation brings each component into its negative, right? So if I operate I on xyz, it becomes minus x minus y minus z. Now if we compare S2 to the power 1 or S2 operation with this inversion operation, both leads to the same result. So we can say that S2 operation is none other than inversion operation. So we usually write inversion operation rather than S2. S2 is not usually written separately, but it is usually written as inversion operation. So the improper axis of order 2 is usually referred to by its name, center of inversion. The second operation associated with S2 is S2 squared. So this S2 squared is sigma h square into C2 square. Both are identity, so that leads to identity operation. Therefore S2 to the power 1 is inversion operation and S2 square operation, second operation, is identity operation. That's all about the different symmetry elements and symmetry operations present in a molecule. Now we will discuss how we can combine two or more symmetry operations. Maybe I will discuss that in the next class.